please ask me, okay? So, Hong Wei, yeah, you got the Chinese name, so I'll just, good, I know you, okay? So, please be back, okay? Only Hong Wei reply to me, others there? Okay, good. So, let's continue our study, okay? Will be in let's say you ask a lot about the quiz one, all right? Yeah, MCQ, what? Yeah, next Thursday will be September 29th. Yes, September 29th. Yes, exactly. Is that okay for you? Yeah, it should be no problem, right? Okay, so let's continue our study. We just finished the calculation of pressure. The resultant force straight plane. It's easy. It will equal to the pressure at the centroid. I mean, the magnitude. The location, you should use the moment equation, or you just use the formula directly, okay? So, but actually, in reality, not all cases are just um, uh, straight. Sometimes we just, keep linear, right? And here we got another example. It's simple. We got two fluids. Okay. This water dam is shown in this figure. The upper part is water with specific weight of gamma 1. The lower part is cement with specific weight of gamma 2. Please find out the resultant force that the fluid acting on the water dam with unit weights. Here, we got two fluids. Okay, so what would it be? The first part is water. So its pressure loading should be triangle, right? And for this, we just only calculate the width here. Okay. Calculate the magnitude here. So for this water, F1 will be F1. F1 will equal to the pressure at the centroid, right? For this part, for this plane, times the area, right? And so what will be? The pressure at the centroid should be gamma 1 H1 over 2, right? The area will be H1 times unit width. Okay. And the question about this one? This should be F1, right? By the water on the dime. Okay. This will be the resultant force by the water acting on the dime. How about the specific weight? How about the specific weight? The specific weight, just got to, for the cement. So the pressure loading, what's wrong? Right, should be trapezoidal, right? And so F2, where you could to the pressure at the centroid of this plate, right? And so PC2, just I need to get the phone, just 1 second. sorry, because I just got a phone from my mom. Okay. I'm sorry. Okay. Now, the force by the cement on the dam will be calculated separately. Here is you should be very careful. F2 will equal to PC2 times A2, right? A1 PC2, C2 centroid of this section, this segment. So how to calculate PC2? PC2 will equal to, what will be? PC2 will equal to be the pressure at this interface plus the pressure by the cement, right? So it will be gamma 1 H1. Gamma 1 H1 is actually the pressure by the interface, right? Plus gamma 2 H2, right? This is equal to, right? And then the area will be H2 times 1. Okay, so this F1 plus F2 will be the total force, Okay, here, total force on the dam. This one is the force by the water, and this one will be the force by the cement. Okay, here actually is gamma 1 H1 is the pressure at the interface plus gamma 2 H2 half H2, right, will be the pressure at the centroid of this segment and then times area, okay? So this is the total pressure force. Here we only calculated the magnitude. It's possible to find out the location. It's possible to find out the location of the total pressure. It's possible to find out the center pressure. How can we do this? We still use the moment equation, right? We can find out for this segment, we can find out the pressure, the reacting pressure, the resultant pressure P1, right? Or F1, sorry. We can find F1, the acting point. And for this trapezoidal, we can find the acting point F2. And then we use the moment equation, the total moment of the resultant force will equal to the summation of the moment by F1, F2. For example, you can choose the origin. Oh, okay. So this one will be your online assignment. You need to find out the acting point. You need to find out the acting point of the resultant force that the fluid acting on the water dam. Okay, you need to, later on, you need to find out the acting point, or you need to find out the center of pressure. You need to find out the center of pressure. Okay. Okay, let's continue studying. I just had drawn static forces on curved surfaces. 2D curved surfaces, so we just only derive the equation for 2D curved surfaces. It can be also applied to 3D curved surface. What's 2D curved surface? One curve doing a translational movement. You know, translation movement, it will always parallel to its original position, will create a 2D curved surface. Okay, this is a 2D curved surface. And we got a lot of engineering application, just like radio gate, oil tank, double curvature arc dam, and how to calculate the pressure force on a curved surface. Here again, just like BC is curved surface, we need to calculate. We need to calculate the force. Sure, definitely, we know we still can use the integration method. We took the differential area and then we do the integration and we can find the total force. Okay, but however, that will be a little bit complicated. So generally, we choose this one will be much easier. We isolate this water volume ABC. We isolate water volume ABC, and then we draw FBD on this isolated fluid volume. We will say AB. Just you can assume that AB is here. You got upper surface, right? AB. AB will have the force by the upper fluid, right? F1, and F2 will be the force by the left water. FH, FV actually we will have also have force acting by the curve BC, by the curve wall, by the BC to the fluid volume, right? We use its horizontal and vertical component to indicate the force, okay? Except this, we also got the weight. Okay. So for this isolated fluid volume, we draw FBD, the force by the upper fluid, the force by the left fluid, and the force by the curved wall. FH, FV will be the horizontal or vertical components of this unknown force. Okay. Also, we need to consider the weight of the fluid volume. This will be the FBD of this isolated fluid volume. Use what we have learned in equilibrium rigid body. And so according to the equilibrium equation, in horizontal, we will have FH equal to F2, FV equal to F1 plus W, right? FH in horizontal, if we just establish x-axis, y-axis, so in x-axis, we should have FH minus F2 equal to 0. So that's H equal to F2. Or it's say the horizontal force component by the curved wall to the fluid volume will equal to F2. F2, how to calculate F2? Is it possible to calculate F2? AC. AC is actually a straight plate. It's not curved, right? AC is a straight plate. So how to calculate F2? F2 will equal to the pressure at the centroid of AC, right? Centroid of AC times the area of AC, right? This one, easy, because AC is a straight plate. FH equal to F2. In vertical axis or in y-axis, we know we got F1, we got W, and F1 plus W minus FV will equal to 0, or FV equal to F1 plus W. That's say the vertical component of the vertical wall to the fluid volume will equal to F1 plus W. W is the weight of the fluid volume. After we find out FH, FV, why we got this? Action and reaction force. FH, FV, we got FH prime, FV prime, right? FH, FH prime, FV, FV prime, action and reaction force. FH, FV actually are the force, are the horizontal and the vertical force by the wall to the fluid volume. So Fh prime, Fv prime will be the force by the fluid volume to the vertical wall. Okay, so in magnitude they are equal to each other, but in direction they are opposite to each other. Okay, so after we find the horizontal component, vertical component, we can find out the resultant force to acting to the curved surface. So Fr will equal to Fh square plus Fv square and then square root, right? So this is how to find out the hydrostatic force on curved surface. We just choose an isolated fluid volume and draw FBD and apply the equilibrium equation in horizontal and vertical direction. And then we know we got it. We obtain Fh equal to F2 and V equal to F1 plus W. Fh equal to F2 is easy to calculate because uh, AC is actually a straight plate. So it can be calculated directly by what we have learned. F2 is equal to the centroid of AC times the pressure at the centroid of AC times the area of AC. And this one is equal to the horizontal component of the vertical, of the force on the vertical wall. Okay, on the curvature. Okay, on the curvature BC. Okay, and how about FV? FV is equal to F1 plus W. Okay, so let's say FV. So, sorry, we use still here. It would be easier for you to understand, and then we do the conclusion. Okay. So FV equal to F1 plus W. W is the weight of the fluid volume. How about F1? F1 is equal to gamma H times AB, right? Because AB will be uniform pressure loading, right? So P will equal to gamma H A. This is HA, right? Times its area. This will be the force, right? And how about gamma HA times AA? Is actually equal to the weight of this fluid column, what? So F1 is actually the weight of the fluid volume, the fluid weight by the upper column, right? And plus the W plus this is the fluid weight of this ABC. So how about FV? So FV is actually equal to the weight of the pressure volume. Later on, we will see what's pressure volume. Okay, we'll call it that here. Horizontal force is equivalent to vertical plane force. This will be the curved surface, and then its horizontal force will equal to the force on this plane, right? This is A2. Okay, A2 equal to AX. Okay, Fx equal to gamma HC AX. HC is actually the centroid of AX. Okay, and vertical force is equal to the weight of fluid directly above. Okay, the weight of fluid directly above. This is gauge pressure. Sure, we can plus free surface pressure force that will be absolute pressure. And V equal to gamma V. Okay, V will be the volume of the of the fluid directly above the curved surface to the free surface, okay, FV. After we find out the force by the vertical wall to the fluid volume, use action and reaction forces, so we can obtain the force by the fluid volume to the curved surface, right? Just here, we can do the same thing, right? There's the curved AC, okay, and then we can choose this isolated fluid volume, and then we just can draw its FBD like this way: the weight of the fluid volume and the horizontal force by the white fluid and the force by the upper fluid, and this one here, this will be distributed force by the curved surface to the volume, and we use its horizontal and vertical component to represent the resultant force by the curved surface to the fluid volume. So again, we can have the equilibrium equation in x-axis. We will have FH equal to Fx, right? Again, the horizontal component equal to Fx equal to the force acting on the projection area BC, right? Will equal to the pressure centroid of BC times the area of BC, right? It's easy. And also you can find out its acting point. You can find out the location of the resultant force on BC. And FV, what will be FV? When FV in y-axis, FV again is equal to Fy plus W, right? And W is the weight of this fluid volume. Fy, this one is again is equal to the fluid volume of the fluid directly above, right? So F1 is equal to gamma HA times AAB. So finally, we will know FV is equal to gamma, the volume. This is a volume. This volume is actually the volume of the fluid above the curved place to the free surface. Sure, you can find out the angle of force. You can find out the ratio of the vertical component and horizontal component. Okay. How about this one? For this case, we still do the same, right? We do the same, sorry. Just like this case, okay? We will have this, the curved surface AB, and we still can isolate fluid volume. This is isolated fluid volume, and then we draw FBD. This will be the F1. This will be F2, and here F1, and horizontal, vertical, and the weight. You can still write down the equilibrium equation in horizontal, Fh equal to F2, right? The horizontal equal to F2 is actually equal to the force on the acting on the projected area. Okay, the project area, the force will equal to the centroid of the project area times the projected area. Okay, And FV will FV for this, FV will equal to FV will equal to from here will equal to F1 plus W. This is F1, right? The fluid weight. And so this is the weight of the fluid volume. So again, it will still equal to the weight of the fluid volume above the curved surface to the free surface. So this is we call pressure volume. Okay, pressure volume is the geometric volume and it has no relations with that whether there is a liquid in it or not. Okay, why we see this? For here, this is curve AB. We have real water here. So we can do the same. You can do the same, isolate the fluid volume and then draw FBD. You will find FV is actually equal to the weight of the pressure volume. Pressure volume is actually is the volume from the curved surface to the free surface. But for this case, for AB, the water is in the left side, but here the force, the vertical force, is also equal to the weight of the pressure volume, which is actually there is no water here. Why? Let's say this way. Okay, we isolated fluid volume like this way. So we draw FBD for this ABC. Okay, so we have F2, F2, we have F1, right? And we have horizontal, we have vertical, we have W, right? So again, in x-axis, we have FH equal to F2, right? Still the same, the horizontal force will equal to the force on the project area, right? FV downward plus W equal to F1, right? So FV equal to F1 minus W. How about F1? What's F1? F1 is actually equal to gamma HB times area. This one is also the weight of the fluid volume from the bottom to the free surface, right? So F1 minus W, sorry, F1 minus W. I mean, this is F1 minus W is actually equal to the vertical is equal to the weight of the fluid volume. Okay. So that's all for today, but you need to submit online. Submit online just now. I said you need to do it and then submit online of this one. This one. You need to find the center of pressure. Okay. And then after you've done this, submit online and then you can leave. Okay. You need to find the center of pressure of the resultant force that the fluid acting on the water dam. Okay.